Um, okay, so today I'm going to continue telling you some more stuff about the canonical transformations, and also called symplectomorphisms. I think I use both terms, but just as a quick reminder of what was the idea, um, you know, so the we have this matrix, our most important matrix in the seminar. And then the idea is that another matrix in symplectic, a matrix as is symplectic if S J S transpose equals J. Okay, this is a definition that works for any like dimension or any size of the matrix. Of course, like here, when I say any size, we're assuming everywhere the matrices are of even size for this to even be able to be written down. So like when it's not 2 by 2, you just put like the identity of size n by n. Like I can put it like here, right? Like this, like the identity of size n by n and minus the identity of size n by n. Okay, so this is like the correct definition, like for any matrix, so like for any even matrix. So this is for any even matrix. In the 2 by 2 case, which is kind of like the one that we have been focusing most of the times for now, in the 2 by 2 case, is it does translate into just like having determinant one, if you remember. So it does simplify it a lot in the 2 by 2 case. Only require and like some things that for now that happen with these matrices being symplectic, where like, well, for like the structure of these matrices is like, if S, like maybe just let me put some here, like, so if S is symplectic, then the transpose, also the inverse are symplectic, that's kind of important, useful. And again, this is true for any even size. And also that, well, the identity is symplectic, that's kind of easy to check here. And then if S1, S2 are symplectic, their product is symplectic as well. So it's S1, S2, and also identity is symplectic. Well, this is the identity of size 2n times 2n, right? I mean, so again, like for those who have seen this, like it's just like these are the conditions for like the symplectic matrices to form a group. Not that we are going to use that too much at the moment. I mean, like usually the definition of a group, like there's nothing about the transpose because like a group doesn't have like an operation of a transpose. So usually the definition of a group is just like about it's closed under multiplication. So like if you multiply two elements, you get another element in the group, and also that the inverse of any element is inside the group again. So it's a little bit better than just like an ordinary group because also the transpose happens to be symplectic. So that's why like it doesn't matter, like this may be slightly different of how I wrote this last time because the fact that like the transpose is satisfies this condition whenever S does means that you can also write this also as S transpose J S equals J. So it doesn't matter like at the end of the day whether you put the transpose in the first factor or the second factor. Okay. Um, and the point of these matrices is that those were the ones that we found if we did like a linear change of variables, right? So the idea was like if you had defined like xp as x prime p prime, like so you just think of xp and x prime p prime as two different sets of coordinates, then like the equations like of Hamilton like get preserved provided S is symplectic. So if S is symplectic, you had the, the x dt equals what, like the partial of x with respect to p, and dp dt equals minus a partial of h with respect to x. If and only if, I mean, like the idea is like, yeah, like the form of the equations is the same. So you can write like, the equation. Let me consider some very good questions about this. So that's kind of what we were discussing before. Was useful. Okay. So the way I'm selling you these like these matrices is kind of like well, they arise because you want the equations to look exactly the same in both systems of coordinates, right? So the way I'm presenting this is more like from the perspective of the coordinates, that they about like a coordinate transformation. But these matrices also appear when you think about what the behavior of the solutions. So let me see if I can explain this like more concretely. So let me do it. Like, this can be proven in generality, but I don't want to kind of get it too bogged down into like a lot of like vector fields and like what's the flow of a vector field and things like that, because it's just like a little bit of like extra notation which can be over the top. So let's just work out like a case which is kind of like illuminating. So here's yeah, in fact I'll do it okay, so here's like a quadratic Hamiltonian. So I'm just going to assume that the Hamiltonian, like again, like think of this as a function of x and p. So I'm just going to assume that kind of is as simple as it can get, more basically. Well, the easiest thing would be linear, but that's a little bit too simple. So I'll just assume that it's something like a x squared plus 2b xp plus c p squared, where a, b, c are constants, right? Okay, so hopefully this looks familiar, right? Because this is just like a quadratic form, right, of those of linear algebra. So there is a better way to write this, which is just like this. That also explains my choice of the two here, right? Because then you write it as in this way. Right? So so there's like a 2 by 2 symmetric matrix associated to this quadratic form. Just for because of annoying, I mean, there are kind of like factors of 2 hanging around everywhere here. So I'll just define I'll just write this instead of calling this matrix H, which I could like not call HM, and is here for matrix. So it's kind of like the matrix associated to H. So like I'm going to distinguish between the matrix and H, which because H is like a function. So, but obviously it's related to H. So I'll just call it H sub M. And I'll put a 2 for now, which looks a little bit stupid, but you'll see in a moment why it's convenient to have, redefine it like with a doubling every coefficient. So in fact, if you write it this way, and if you call z xp, right, then better you can write this as 1/2 p transpose hm c, right? So like, I mean, yeah, like you have to cancel this too, so I just need put in 1/2. It's just that looks more closely to, for example, if you remember something like where did it work? Had I written this one before? If you think about the harmonic oscillator that we had talked before, it was really like p squared over 2 plus x squared over 2. So again, like there are factors of 2 kind of like everywhere in place. So it's when we take derivatives, there will be a 2 coming out, and so it's better for it to cancel this 1/2 that I just wrote in front. Okay, so that is what the Hamiltonian would look like. Okay, and then we can find the like what the Hamilton's equations look like in this case. So okay, so let's see. There's questions so far. Right? Okay. So what were the equations of motion? Like, if you want to write them this way, I mean, right? I guess I had introduced. I'll put it everything still with vector notation. So if you remember, like, the way in which to write the equations in terms of matrix notation was J times the gradient of the Hamiltonian. So this would be you know, 0, 1, -1, 0. And what's the gradient in this case? So the gradient, so it's a derivative with respect to x, a derivative with respect to x, this gives you 2 ax plus 2b p, right? And then like the derivative with respect to p gives you 2 px plus 2 CP, right? So you see like there are like all these factors of 2 that show up. Where did I write this? Here. Okay, and that's just the same. Okay, so you can write this way. Well, you can take out like the twos everywhere. So 2, 0, 1, -1, 0. And it's like, and then you get A, B, B, C, X, P. Right? That does give you the same thing. Okay, so that means that if you it's as a system of equations, like the Hamilton's equations, like if you like go back to this like formula, just become this. So that's why it's convenient to have these two, having the define the matrix here with the two, because then I can reabsorb the two into the matrix. So it's just J H M C. Is that okay? Is that make sense? Um, that's looking good. You're thinking about something that I don't know. That look. I mean, I'm just trying to rewrite it in a way that looks identical, like a system of ODEs, right? In matrix notation. By the way, so what? Like this actually works not just in the 2 by 2 case. So in the in that 2n by 2n case, let me just put it as an aside. When it's 2n by 2n, well now you think of x as being x1, x2 up to xn, and p as being p1, p2 up to pn, right? And then if you want to generalize this, the generalization of like this quadratic case would be like there's like an obvious analog of like this vector z. There's like z. Oops, there's a transpose here. There it is. Yeah. But I know here HM is like a symmetric 2n by 2n matrix, where HM is symmetric and 2n by 2n. Okay. And here, like like the equations will like formally, I mean, it's exactly the same calculation basically. So the Hamilton's equations just look like this. Okay, so it all looks like the same. that's like the convenience of like introducing the matrix notation so that you can just write it in the same way regardless of the size. The nice thing is that this is just like a matrix. So like if you remember from ODEs, like the solution to like the linear system is just the exponential of the matrix. So the solution to this as a function of time, so the solution is just e to the tjhm times the initial, like the initial position momentum. So let's put it like z naught. Okay, so like maybe I should do like a picture here somewhere. So what I'm saying, like if you want to think about it like more with some picture, is that like you have like the like the solution to this equation, since it depends on time, is just some curve in space, right? So like imagine that like the initial momentum and position is somewhere along this, there's a point on this curve, right? Which is what I'm calling z naught. And so what I'm saying is that the position and momentum at time t is just like the exponential of this matrix times c naught. So like time, like the configuration, the state at time t is related to the initial values through this exponential matrix. Okay. Now the cool thing is that this exponential matrix happens to be a symplectic matrix. So that's what's kind of like fun here, because what this means is that let me write it down. So if you define S of t. Okay, so this is like a matrix that depends on time, right? So what I'm claiming is that for any real number t, right? So for any t, S of t is symmetric. Sorry, it's symplectic. Symplectic. So meaning that, like, like the way we thought about symplectic matrices is that they transform, old coordinates into new coordinates where the equations look the same. But what this is saying is that also, what relates the vector, think of this as a vector, what the matrix that relates the vector at time t with the vector at time zero is also symplectic. Okay, so like the symplectic matrices kind of have two different roles. Like one is kind of like in terms of this change of coordinates interpretation, but also it's kind of like in terms of how do you relate the state at time t with the state at time zero is through like a symplectic matrix. Is that making sense? So it's kind of like I don't think necessarily you had to believe that had to happen like just from how like a symplectic matrix was defined, right? But it is like a key thing. So what I'm going to do now is actually just kind of show you why this is true. Okay. It's like it's a cute trick because it's just like a good excuse to play a little bit with the properties of the exponential of a matrix, which is always like a good exercise to have around. So what does in the 2x2 case, it's easy to check. In the 2x2 case, like let me just write it as a remark because it's very explicit to check this. So in the 2x2 case, but I'll prove it in more generality. In the 2x2 case, what we need to see that the determinant of this matrix is 1, right? That was a condition for being symplectic. We need to check. Right, but I don't know if you remember from last time, the determinant of the exponential, right? What was the determinant of an exponential? Is e to the trace of the matrix, right? Like I've showed you the trick last time, and it is easy just by brute force, like to do the multiplication and check that this matrix has trace zero. Like that's not like a very complicated thing. Like everything's super explicit. J is 0, 1, -1, 0, and HM is like A, B, C, D, but A, B, B, C. So like it's easy to check. I do it in the notes. Like I have to upload the new version of the notes, but it's like it's like not like a bad calculation. The trace of J HM equals 0. Okay, so that is not too bad. So like that in the 2 by 2 case, that's what tells you that these have determinant 1. What's more fun is to try to verify this, like with the actual definition of being symplectic, because that is like a more, again, it's like a more fun exercise in properties of like the exponential and linear algebra. So what like in the general case, in general, what do we need to check? That for every t, we need to check that for every t, s of t time. What was the definition of symplectic? Is that s j s of t transpose, right? Equals j. In fact, like if you want, I will write the t as a subscript, so that is like less like annoying to the eyes, right? So it was just that if you do as j as transpose, you get j back. That was the definition of symplectic, and we have to check that that works for any value of t. So if like here's like a fun way to do it. Like if you be one way to check this is to see what happens like at time equals 0. So let's see what's at t equals 0. At t equals 0, what is s of 0? Like it just puts a 0 here, and e to the 0 is like the identity matrix. This is still true. So no, obviously, here like the zero matrix, but that's just the identity. So this is true, right? Because like identity J, identity transpose is J. That's fine. Okay, and that makes sense because if you think about it, at time 0, you're asking what connects the position momentum at time 0 with the position momentum at time 0. That has to be the identity matrix because they're not doing anything, right? So that's fine. And then what I'll check is that what is fun to check is that the derivative with respect to time is of this is 0. So this is what we're going to verify. Now verify. Now check that. It's one of these things that if you're not until you see it, like once you see it, it's okay, sure, like it makes sense to try this. But if you haven't seen it before, it's not super obvious. Why would you start this way? So like, if you check that this is a zero matrix, that means that this had to be constant, right, independent of t. But we already know that its value, like you already know that this like equation holds at time 0. So like that would then like everything is out. Okay. Is that making sense? So, like, let's do that. Let me put the definition of the matrix S of t here at the top before I erase this part. So S of t is e to the t j h. Okay. So what is the derivative with respect to time of that thing? Okay, it's just like the regular product rule, which also works for matrices, right? I don't know if you have done matrix analysis, but it's essentially more, I mean, many things are just exactly the same regular formulas without one. So the product rule is just like the derivative of the first factor times the remaining factors, right? The good thing is that the one in the middle is constant, so we don't have to differentiate it. That saves a little bit of time here. And then the taking derivatives commutes, or like, you can move that inside the transpose. So I also, so like by the prior rule, like then you do nothing to this factor times the derivative of the second factor. Uh, is that okay? Okay, so it's just like a question of what the derivative of the exponential, like the derivative of the exponential, like maybe let me write it here before like doing it for this particular case. If you have a matrix, right? What's the derivative of the exponential? It is what you would like it to be, right? It's exponential times the argument, like, the derivative with respect to t of the inside. So it's e to the ta times a. And the cool thing is that a commutes with the exponential. So actually there's no ambiguity here of whether you put a as the first factor or like the second factor. So this is actually the same as a times e to the ta. The reason why a commutes with the exponential, like actually in that case, it's more easy to see it from the power series expansion, because if you see it from the power series, everything are just a bunch of factors of a. Like you just have to justify that you can take limits, like whatever, blah. But that works. Is that okay? So here A is like J times HN, right? For this particular case, for this application I have in mind. So you get, um, so you get the exponential itself. So in fact, like, like, let's put it with the exponential, that's fine. And at times the derivative would be A, which is JHN. So in this case, it's more convenient to put it here. I believe that's what I wanted to do. And then J. Let me see. I mean, I can, if necessary, I can move it around. And also, oh, another important thing about the exponential is that it commutes with the transpose. So e to the a transpose is e to the a transpose, and that makes sense again from the power series expansion. It's kind of believable that that should be the case. So like transposing here is the same as okay. And let's see, there's something similar happening for the other one. So e to the st is e to the t g j h m. J is here, and then I just have to transpose exactly this thing. So just, I mean, right, I could have transposed like things like before. So I'll take, let me see. Okay, I'll put J H M transpose. I may need to move things around. Trying to decide whether. Okay. That making sense? So far, so good. Every step, is that okay? So let's see. Okay. Let's just think about what yeah. This is going to be fine. So okay, so term is in common. You can factorize it from the left, right? So you get e to the t JHM. And then this term is common, so I'll factorize it from the right. Right? So that's fine. This is fine. Okay. So what do you get here? You get J HMJ, right? That's what survives here. And here you get J. Okay, so when you transpose, you have to transpose the product, right? And so we almost have it. So HM, like by assumption, the matrix is symmetric, right? So this is really just what is it? The JHM, right? And what is the transpose of J? Let's see that. Like J, like if you remember, like J is a zero matrix identity minus identity zero matrix, right? So what is the transpose? It's actually, well, minus J. The transpose is minus J. So it's in fact skew symmetric, right? This matrix is skew symmetric or anti-symmetric. I don't know what name you prefer. Oh, so cool. So this becomes minus J. So you get J, HM, J, J, HM minus J. So it goes like, like this goes like, cancels out, gives you zero. So, or the zero matrix. So it doesn't matter like these two factors because you have zero in the middle. So that tells you that when you have like what it means is that if you have a solution, like if you have a point in phase space and you evolve it using the Hamilton's equations at time t, that point is related to the initial point via symplectic matrix. Okay, so like again, a symplectic matrices can be thought about as, oh, you are transforming the coordinates in the phase space, but also like it is what relates the transformations at like the point at time zero with the point at time t, if that makes sense. Is that okay? So far, so good. Okay. So like in fact, like just as what name for this trying to find the phrase. I mean, just as the idea, like I'm doing like a baby version, what will happen in quantum mechanics, because in quantum mechanics, what will happen is that you'll have so let me do like a quick comparison. I'll motivate this a little bit like that later. So like what here, like what we were just doing is that if the Hamiltonian happens to be like given by in terms of like this symmetric matrix, right? Then the equations were linear, right? Like now I'm getting this. So the equations were linear, and this is happening in R to N, right? Or you think of R to N as Rn cross Rn, and you're thinking like the coordinates for Rn to be X, and the coordinates for Rn, the other factor of Rn to be T, right? So, and this, it is like e to the tj hm z naught, right? So that is what I'm giving you in this case. This is finite dimensional in the sense that the space itself is finite dimensional. So this is like the classical mechanics picture when the Hamiltonian happens to be quadratic or happens to be in terms of like a symmetric matrix. The important thing here is like this, so it was a matrix, symmetric. So like in the in the quantum mechanics version, I mean, like there's different ways to set it up, but like if it, like the most direct analog here would be in what's called like the Heisenberg picture, like not the Heisenberg picture, like the matrix mechanics picture, where you're working instead of R2N like R infinity, meaning that like not like countably many products of R. That like like again, you have to do some. There are different ways to set it up, so I'll set it up once we get there, like in a better way. But so instead of that, what you will have, is that this vector has infinitely many entries, like so it's a sequence that which you can identify. So like I'll just write it at psi. So like now this has like infinitely many entries. So it's some subsequence, like I'll call it x1, x2. Well, just do not be biased. I'll call it I'll call the coordinates here just to kind of be more fair. Like well, yeah. What's another? Oh, U1. Yeah. U2, U3, U4, blah, 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 up UN, and it continues forever, right? So the vector now has infinitely many entries, and you would have something like this. Okay, so here something that actually, this should I? Yeah, it is kind of like an infinite dimensional space of. I think this analogy is more appropriate to think about it with the entries being complex. But like again, I'll set it up in a different way later. But the important thing here is that J, if you remember, I told you like this squares to the identity. Sorry, it squares to minus the identity. So it's kind of like the number negative I, right? Because I squared is -1. So the analog, right? So J secretly is like some sort of like I or minus I, right? Like I and minus I both squared to -1. So here, like in this version, J gets changed to minus I, and the Hamiltonian becomes a symmetric matrix in this in this space of vectors of infinite entries. So like when you do that, you call it like an operator. So just call it like H hat, like hat for operator, or like you just want to think about this as an infinite matrix of infinite columns and rows. Okay. But the equation like looks exactly the same as this one, and this is now called Schrödinger's equation, basically. This like you can set it up so that it looks formally the same as what we have here, and then you find from there like the psi of t is like just be almost by the same logic is e to the minus it h hat psi naught. So again, just because I is playing the role of j here, so or negative I should say. So it's like essential, and that tells you like that, and telling you quantum mechanics how the wave. This is called the wave function. So it tells you how the wave function evolves in time in terms of the Hamiltonian. So you exponentiate it. Okay, that's basically what happens in that case. The thing is, like, there are more interesting things that happen here, which don't necessarily happen in this case. So, like, again, we'll get there once. I'll tell you once we get to the quantum mechanics part. But one of the things that happens is that this matrix is what's called is unitary or also orthogonal, and that means that it will preserve the size of the vector, which doesn't necessarily happen here. So, like, I won't get into the calculation now because we won't use it now, like up to later. But like it's on the notes which I'll upload today. But it is not so bad to check that, when you have something like this, the norm, like the Euclidean norm of this vector, may not be the same as the Euclidean norm at time 0. So like, that makes sense because if you remember, so if you remember the harmonic oscillator, there is evolving in circles with the conventions that I had used, and that does have like the same norm. If you move along the circle, like the norm with respect to the origin is the same. But if I had used different constants for the harmonic oscillator, it would have moved like an ellipse. And if you think about it, a vector on an ellipse will change its size with respect to the origin, right? So like the length of the vector as it evolves in time is not necessarily preserved in this case. But what will happen in quantum mechanics is that this is always preserved in time. The norm of these vectors is always preserved in time. So, which is kind of nice, because this later gets related to like the probability interpretation of what this is. But yeah, but really, like what you can think in a sense is these quantum mechanics, whatever it is kind of like a version of exactly this picture where like now the vectors have infinite entries. Like really, the equation is formally identical. Like there's no difference in the equation, like or anything like that. Sorry. Let's see if there are any questions about this. So let me tell you a little bit. Okay, so before like maybe moving on, because we'll use that in a moment. So today should finish at 11:45. Yeah, so what I like about these examples is that everything is very down to earth. You can really see with your eyes what's going on instead of like using a lot of theory, just in case. So just like as a reminder, so when I originally defined being a symplectic matrix, right, was something like in this setting where like the coordinates xp were in terms of the coordinates x prime p prime. So this is like a linear change of variables, right? So this is like a linear change of variables. So in like the nonlinear case, right, like if it's just like a general coordinate change, like for example, like polar coordinates, like the way polar, x, y are related to r theta is nonlinear, right? Because it involves strict functions, cosine of theta and sine of theta. So that's a nonlinear change of variables. So when like x, p are just functions of x prime, p prime, so like, in the nonlinear case, when you think of x as a function, I'll write it like this. So now xp are related to x prime p prime, like just by some functions. Then you want to say that what ends up being the right definition for what it means, like the change of variables to be canonical. So this is like a canonical change of variables. If the linearization of this transformation, which is the Jacobian, if the Jacobian is symplectic, it's a symplectic matrix. Because remember, the Jacobian is always a matrix, so you can ask for that to be a symplectic matrix. So what was the Jacobian? I mean, it would be kind of like the way I can write it like this. So you want these matrix to be symplectic, And in the 2 by 2 case, like, okay, so that really just means, okay, just terrible notation because it's the same J as for 0. Okay, so what is another, okay, now I'm getting stuck because I don't know what to call this if I don't use J for Jacobian. Let's call it, L for linearization. So this is like L Jack for Jacobian. Okay, so this is like the Jacobian matrix. So this one. So like if you wanted this to be symplectic, that just means that precisely the condition that I gave you before. which in the 2 by 2 case, like just means that the Jacobian must have determinant one. So in the 2 by 2 case, 2 by 2 case, then we must have, then, and the Jacobian must have determinant one. Okay. So like that's kind of like the extension of being symplectic or canonical. I guess you call them more like canonical and transformations in this case. So it's a canonical transformation is the determinant is one. So just to maybe it's good to do like an example here. Um, If you remember when we had talked about the harmonic oscillator, it was like x squared plus p squared over 2. Okay. And I had done like two changes of variables. One like was kind of like polar, right? Like where x equals like r cosine of theta and y equals r sine of theta. Sorry, not y, p. So this was like a change of variable, but this is not canonical, right? Because what's the Jacobian in this case? So the Jacobian would be x r x theta p r p theta. Okay, and then this gives you cosine of theta. Um, then gives you minus r sine of theta. And then sine of theta. Right, and then r cosine of theta. Right, so the determinant of this has determinant r cosine squared plus r. So like just got determinant one, which is not, like this depends on the radius, so it's not one. This depends on r, so it's not a constant determinant equal to one. So this was like, so that's why like the equations looked bad when we had changed to these coordinates, but then there was this other coordinate system we had done. So there was this other coordinate system we had done where I was just like r squared over 2, if I don't remember, if I'm not incorrect about this. So 2i equals r squared. So r is root of 2i. So, if you do these other coordinates, so x is like root of 2i cosine of theta. Y is root of 2i sine of theta. Okay. Is that making sense? Yes. And then, yeah, let's see if this one works. Like I'm making a mistake. So what is dx di x theta? X with respect to I. Okay, so it gives you stupid root of 2. So root of 2. Oh, sorry, I'm gonna keep putting y there, so root of 2. Mhm. Okay, hopefully this works. Oh, yeah, I think it does, right? That's the determinant of this. So yeah, like the root of i's cancel. This root of 2 with root of 2 becomes 2. Okay, so there's like I think I'm doing like like I do want to get 1, not 2, so there should be like a rescaling happening here that
You should get one because at the end, you can just use the trig identity. You get
Oh.
cosine squared and plus sine squared, and then that.
Oh, yes, feel so stupid now. Right. Yeah. Like these just right. Like the point is that factors of root of I cancel, and then yeah, this like yeah. So it just gives you cosine squared plus sine squared. Perfect. Yeah, thanks. So stupid. Okay, what did I do wrong? Right. So this one was canonical. And if you remember, like, okay, so the difference is like in these coordinates, the Hamiltonian just looked like r squared over 2, right? And in these coordinates, the Hamiltonian looked like literally just I. And this did have like the right behavior for like, for I and theta. So it's kind of like, an interesting thing like that, to see this explicitly. So it does work that way. Maybe the last thing that I wanted to say, unless there are other questions here, but we can move on. Okay, so last thing, just to finish quickly, is introduce this thing about the Poisson brackets, which is also like a cool thing that happens, and it's important once you get to quantum mechanics one more time. Because so far, I guess it may not, like, this is like a perfect example. So we know, so what I'm saying here is that I theta, like I theta would be canonical, so I theta are canonical coordinates. But okay, this is like a nice one because it's like, if you start with x and p, if you think of one is position and the other is momentum, these are like have like a completely different flavor, right? Like these coordinates kind of like mixed together, right? So if you think about it, like this is like x squared plus p squared over 2, right? So these coordinates mix together position and momentum, right? So they don't like, I think someone had asked me about this before, like they don't really have like an, when you have like this phase space, when you have different coordinate systems, they don't necessarily have like an obvious physical interpretation. Like even though maybe ones that you started with, you can think of as position and momentum, when you talk about x prime, p prime, they can have completely different like meanings, right? So because of that, if you, I'm just saying these are canonical coordinates, it's not super obvious, like, which one is kind of playing the role of X and which one is going to play the role of P here. Like which one is, that's what physicists call generalized position and generalized momentum. So which one is kind of like the general, like which one is kind of like, playing like which role. So this kind of gets clarified a little bit more with the Poisson brackets. So like actually the Poisson brackets give you like a better sense of what's supposed to happen. So let me tell you what that is. If I can erase here. So the Poisson bracket, okay, so the Poisson brackets, to define them, let me remind you that like I had given you this definition of the matrix omega from last time, which was like called the symplectic form. So this was just U transpose J B. Okay, so that was the symplectic, this is sometimes called the symplectic form. And then for the Poisson brackets, so this is defined like this thing is defined for vectors, right? You need things that are vectors here. And in fact, if U was like U1, U2, right? And B was B1, B2, it really was, and this ended up being U1, B2 minus B1, U2. Like it was really like the area of the parallelogram with sides U and B, if you remember that definition. Okay, so now imagine that you have two functions of x and p. So now suppose two real value functions. From phase space. So the idea is that there was some bracket is defined. We're going to use a symplectic form to define it. So this is called the Poisson bracket of f and g. And how is this defined? So and I'll show you in a second why this is like a natural definition, but I think it's better to start with the formula. So the idea is that if you have two functions, like for each function, you can take its gradient, right? So you take the gradient of the function. And these are now vectors, or well, vector fields, strictly speaking. So these are vector fields, so you can plug them into omega. So you feed these to omega. Okay. So in other words, this is the Poisson bracket is the gradient transpose J times the gradient of G. Or if you prefer to think about it more like in terms of like something more explicit, where the gradient, what is a gradient is like the derivative of f with respect to x, derivative of f with respect to p, and same for the gradient of g. The definition of the Poisson bracket is just, it's this same definition is like there is partial of f with respect to x times partial g with respect to p minus the partial of g with respect to x times the partial of x f with respect. So it is like in the plane, it is the third entry of the curl. Wait, let's see. Yeah, if you think about this, it's kind of like an overkill, but like you can think of, let's see if this would, no, it's not really, it looks like a curl because I suppose for the curl, you need like the curl of a vector field. So no, yeah, it's not a curl, but it has like a structure that's similar to a curl. Like, yeah, if you had like, I guess, yeah, if you had a vector field, if your vector field in the plane were like f comma g comma 0, thinking of phase space inside R3, like think of phase space being contained in R3, so you can find the curl of this vector field. Yeah, and then does that give me the right definition? So now, and well, it doesn't matter which third one you put here because there's let's put like I'll put U because it's just like a formal thing, right? So like I'm just trying to check here. Would that give me the right thing? So yeah, like you get 0, 0. Okay, yeah, no, you do need, like, you do need, right, like the curl is just individual, rather like, yeah, so good. It's not the curl, it looks like a, yeah, it has like a formal structure to the curl, but like the curl, it's only single derivatives, at a time, right? So it's not quite the same because like here you're multiplying the partial derivatives. So good. But it is like a determinant type thing. So and like curl is just like a determinant, but yeah, it's not related to the curl. So okay, so you're kind of comparing. If you look, okay, so if you start with this definition, it does look a little bit weird because it's just comparing like the partial derivatives in this odd way. It looks like a bit more geometric from this perspective. It's more natural from this perspective because like you have like two vector fields associated to the function, and then you just like take the symplectic dot product if you like. So you can think about this like omega like some sort of like dot product, but it's like in the symplectic world, right? So it's kind of like the air. So really, this is like the area, right? This is the area of like the parallelogram spanned by the gradients of the functions, right? So at each point you have two gradients. There's a parallelogram with those two gradients. I should do this picture. So if you have a point in phase space, you have two gradients. There's a parallelogram, and the area of that parallelogram up to a sign is like this Poisson bracket. So the area is like this. Then I think that looks better now. Like it makes more sense. Like so, it's kind of like what the Poisson bracket. Like the thing is, like from point to point, right? Like maybe at a different point, the gradients are way bigger, right? Like the gradients don't need to be constant or anything in size, right? So maybe the area is now different, right? So like the pot, like the area could be bigger here or here, depending on what the parallelograms look like. So the point is that these can change from point to point. So it is really like a function of phase space. So this is going to be a new function, right? So this is like a new function. This is like a new function of xp. Does that make sense? So so why are they useful? Because of the following reason. So let's just before giving you some properties that these Poisson brackets have. So the reason why these are useful is like imagine that you have the phase space and you have a solution to the equations. So here's like this is a solution x of t, p of t to the equations of motion, right? And so if you have a function defined on phase space, right, you can evaluate this function along the solution. So you can so if you have like a function xp, you can evaluate it along the curve. Right? And so like its value will depend on t. So you get like a function of t, right? So to get does that make sense? So for example, like the function could just be x plus p or p squared or like p cubed, like whatever function of x and p you think about it, like any polynomial or like any analytic function or whatever. So and then you can ask what's the rate of change of the function with respect to time. So how do the values of the function change as you move along the curve? Right, and this is just like, like the chain rule from multivariable. Okay, now what's the thing? Like if if you have solutions to Hamilton's equations, what is the x dt? That's a partial derivative of h with respect to the partial derivative of h with respect to p. And what's the p dt? That's minus the partial derivative of h with respect to x, right? Because we're assuming that they solve the equations, so the x of t and p of t solve the equations. So this like hopefully looks familiar to this expression. So this is like a Poisson bracket, right? But a Poisson bracket of what? Between two functions, which ones? Just between the f and the Hamiltonian, right? So this is just what this is saying is that if you have a function on phase space and you want to see how it changes along curves, the rate of change along a curve is like the Poisson bracket between the function and the Hamiltonian. So like the important thing about the Poisson bracket is that it gives you like it appears when you want to like know how quantity changes over time on phase space. And it is easy to check. Okay, so let me put this down. It is easy to check that for any function, any f, the Poisson bracket of a function with itself is just zero, because why? If you take f and g to be the same here, I mean, this is exactly the same, this expression is completely the same. So that is why, so what does that tell you? What is the derivative of the Hamiltonian with respect to time? It's a Poisson bracket of h with respect to itself, with itself, because of this result. But this should be zero, and that tells you that the Hamiltonian is conserved along a trajectory, which we already knew, right? Like, but this is like a more like formal way to see that. So that means that h is constant along a solution. So it's like a more elegant way of like checking the Hamiltonian function is like a constant along a solution. Is that making sense? And here's another cute calculation. Okay, so just like here's another fun thing. So what is a Poisson bracket of? This looks a little bit weird. Like let me just I'm almost done. So let me just to not abuse notation. Imagine that the function f is just the function that records like the first coordinate. It's just x. So you could just write this as x. And then the function g, right, is the function that records the second coordinate. So think of them as projections, right? Like the first, like projection on the x-axis or projection on the p-axis. So what would be the Poisson brackets of f and g, which typically you write this as just the Poisson brackets of x and p for obvious reasons, right? Because they're just literally that. Well, if you think of like, this would be like just replace here f with x. So you get like the partial of x with respect to x times the partial of g, but g is p, right? So you get the partial of p with respect to p, right? Minus the partial of p with respect to x times the partial of x with respect to p, right? And so this vanishes, and this is 1 times 1, so you just get 1. So that means that, and this is like a very important thing. So that means that, the Poisson bracket of x with p equals 1. Does that make sense? And the point of a symplecto, like a canonical transformation, right? If you have like a canonical transformation, like if you have a canonical transformation, Or like you think of X as like, as, okay, now I'll use different letters so that it's not confusing, like a function of X prime, P prime, and P as a function of X prime, P prime. Well, what should the Poisson brackets between X prime and P prime be? Okay, like all the details are in the notes, but if you think about what this means, what happens is like a canonical transformation is one where like the determinant was one of the Jacobian, right? So that means like the areas of the parallelograms were one, and this omega thing is literally measuring, if you remember, it is measuring the area, of the parallelogram. So it like the point of a canonical transformation is that it preserves area, so this should continue to be one. Like, so in other words, the point of like, another way to think about a canonical transformation is that it preserves like the Poisson brackets. So the idea is that, so in general, um, if two variables are related, if two sets of variables, xp and x prime p prime are related, via canonical transformation. Yeah, then the Poisson brackets are the same, and so um, and that it kind of like solves the issue. Maybe just to finish in the because this kind of solves the issue, which ends up being regarded as x prime and p prime when you make a change of variables, because it's also easy to check, you know, what if you reverse the order of the brackets? Well, it's kind of like, like it's all these things are kind of like signed areas. So if you put one vector before the other, like you get minus the result. I mean, you can check it from the formula, but from here, everything gets reversed. But in general, and in general, this is like similar to like not just like these two particular ones, but these the Poisson brackets of f and g are negative the Poisson brackets of gf. Um, so what that means is that when you make a change of variables. So for example, when we change xp to like I theta in the harmonic oscillator, right? Because it was a canonical change of variables, that means that one of these Poisson brackets has to be one, either one I theta equals I theta is one, or I theta is -1. Okay, it's for sure like it's going to be one of these two options, and the one that for example, if it's one, that means that this is kind of like x prime and this is p prime, and if it had been -1, that means that theta is kind of like the x prime and I is like the p prime. So depending like of how you arrange the variables, the one that gives so if the first is a correct one, I think it's actually the well actually I'm pretty sure it's this one. So like one can check. One can check that this is the one that gives you one, and that's why you can think of, it makes sense to think of I as x prime and beta as p prime. And that is why as x prime and theta as p prime. So it kind of like the Poisson brackets is like an elegant way of like deciding which when you change variables, which one is playing the role of position and which one is playing the role of momentum, all in quotes. And maybe I should wrap it up. But another thing, like if you have, of course, like it's like hindsight, like not super obvious from what I have said so far, but these things have many similar properties to commutators of matrices. So if you think about it, like what is a commutator of a matrix? Is AB minus BA, right? So for example, like that, like from there, you just get that AB equals minus BA immediately, right? And also that the commutator of a matrix with itself is zero, which also happens like here in the Poisson bracket case. For any function, it is easy to verify. I don't know if I said it already, but for any function, it's easy to verify that its Poisson bracket is zero because what is that? Is the area of a parallelogram whose sides are the gradient of f and the gradient of f. If both sides of a parallelogram are the same, you collapse the parallelogram to a line and that's zero, right? That makes sense geometrically. So these and there's like another identity called the Jacobi identity for commutators, which you may have seen. But the Poisson bracket satisfies like basically the same identity. So what happens like in quantum mechanics is that, like the functions that we are working with in quantum mechanics can transform into matrices, okay? Let me put it like this. Like if you have two functions like here, in quantum mechanics, they get transformed into matrices or operators. And the point of quantizing a system is that you transform the Poisson brackets into commutators. So quantization to a large extent is to, produce like associate like matrices to like these functions. Again, matrices, I mean infinite dimensional matrices. So they become like operators. And then the Poisson bracket becomes the commutator. So for example, what happens, which is kind of weird, but I'll tell you more about that later. So for example, this function, which was like just the x coordinate, the x coordinate gets transformed to like a multiple of the identity matrix, basically, and the position, right, gets transformed to differentiation with respect to x. So it becomes like an operator, like type thing, up to a sign. So it becomes like a derivative with respect to x. But there's like a way to represent like a derivative in terms of an infinite dimensional matrix. Like if you have seen that before, if not, I'll tell you how that works. So that's and then from that, once you compute the commutator here, like you get like instead of getting a one, you get you get like a multiple of the identity, and that's like the the commutators that appear like in the Heisenberg uncertainty principle, etc. Okay, but anyways, let's just end here. So next time, I'll tell you, I think we're almost done with the quantum classical mechanics part. I'll just mention, I think I will need like maybe 2 more classes and then we can talk about quantum mechanics, how that works. Okay, but like you really, from this point of view of Hamiltonian mechanics, many things is just like, okay, quantum mechanics is in a sense like Hamiltonian mechanics in infinite dimensions, like when they're like everything is like in, the vectors have infinite entries, the matrix, like, and like from the but everything formally is very similar to what we're doing. Okay, so let's end here. And I'll see you next week unless